So now we have a circuit. We will see the problem now. So we have a circuit with the power supply, AC power supply, that is 120 volt, 60 hertz. And we have the load with 100 ohm resistance. And now, according to what we discussed about the theory, if the load has only resistance, that's good. It means power factor is equal to 1. The current and voltage, they are in phase with each other. So now if you have the inductor also, or inductance property also in the load, then what will happen? The current is going to lag 90 degree from the voltage. Because of that, the power factor 1 will be reduced. So for example, now if we use some kind of numerical values here, of course, these values you can change to any other value. You can check what will happen because of now we have 100 ohms here. Now we have the 200 millihenry inductance. Because of this, the power factor got affected. That is the theory. So now we have to find how much it got affected. We can use the mathematical the formulas now on the logic. So in order to find that, first you have to find the reactance. So now we have only inductor. So we have to find the inductive reactance. XL is equal to 2 pi FL. So F is the frequency of the supply voltage. L is the inductance value of the load. So 2 millihenry is 60 hertz because it's a American system we are talking about. So if you apply this, then you will get this value. And now you know the inductive reactance. Now you have to find the impedance. Impedance formula Z is equal to square root of R square plus the difference between the reactance XL minus XC whole square. So here we do not have any capacitive property in the load. So XC is equal to 0. So now R square plus XL square. The formula you can rewrite like this. So we know the R value, we know the XL value, just we have found here. You just identify that, you just make the calculation and identify the value of impedance. So now you know the impedance, total impedance of the circuit. And now you have to find the current flowing through the circuit. So what is the formula? The same Ohm's law you can use here. P is equal to I times Z. I is equal to V divided by Z. V is 120 volt, the applied voltage, divided by Z is 125.239. So you will get 0.958 amps. So now what we have found, we know the impedance and we know the current. Now, in order to find the power factor, yes, you can also use some other formulas, but let us find the power factor using the apparent power, true power, and reactive power. So this is another way. So let us say AP is equal to, it is the total power we are applying, VRMS times IRMS. So here we can consider this is 120 volt VRMS, and IRMS we have found already the current flowing through, it is 0.958. So that is the value of the apparent power. Now we have to find the true power. True power means that is the power consumed by the resistor, that is the original load, or that is what actually the load need. That is, we know the current value and we know the R value. You can find the true power. Similarly, you can also find the RP value, reactive power, that is I square XL. So these formulas we had seen just before. So these are the formulas for true power, reactive power, and apparent power. So we are just using the same formulas. And you know I value and you know the XL value you have already found here. So this is the value of the reactive power. So now you can also make the cross check. We know the formula for AP, apparent power, is equal to square root of TP square plus RP square. So we know the TP and RP. So AP square, what? AP you have found already 114.98. So you can just make sure, yes, you just apply the values and use the calculator, and you will find the apparent power, and this way the other right side. So it's not exactly equal, but it's kind of almost equal. So it's okay. Now you have to finally find the power factor. So power factor, we know the formula for power factor is equal to TP divided by AP, true power divided by apparent power. So we know the true power and we know the apparent power here. So apply here, then you will find the power factor value. So here you can see the power factor value is not really very good. It's 0.79. So it means the total power you are applying 114.98 watts to the circuit, but the load is using only 91.809. That is a true power. The load is using only this power, and it means we have energy loss. So then what does it mean? Like 114.98 minus 91.809. So this much of power we are wasting it. And here you can also use the other method, because I mentioned several formulas, right, to calculate the power factor. So we will use this formula now to calculate power factor. So PF is equal to cos pi, right? Cos pi is equal to R divided by Z. R value we know 100, and Z value we have also found here. So we can also find the power factor value. So in order to find the power factor value, you don't need to find all these powers. You can directly use this formula, R divided by Z. So you will also get the same power factor value. Here we have also found the same value. So there are several formulas to find the same thing. Mostly it should be equal, almost equal. So now you have to improve the power factor close to 1. So what was our target just before? We have the load with R, but now we added the inductance. Now we wanted to find out how much the power factor got affected because of this inductance. So this is the result. So the power factor got reduced from 1 to 0.79, of course 85. So now the power factor got reduced because of the inductor. Now we have to improve the power factor. So load has an inductor, it means PF got reduced or decreased. So you pay for 114.98 watts, but the load is using only 91.809 watts. That is a true power. So energy loss is AP minus TP. So this is the energy loss because of the inductor. So, and also this can be identified by using this measure. It's called power factor. So how can you avoid this energy loss? To avoid the energy loss and improve the efficiency, you have to improve the power factor close to 1. That is the goal. So how can you improve the power factor close to 1? So you have to add a capacitor in the circuit in this example. So now I am adding a capacitor, and I assume 70 microfarad. Of course, you have also some formulas and methods to identify the capacitor value. So I have added the capacitor with 70 microfarad to improve the power factor. Before we go into the problem, so you can see here, adding capacitor will introduce new capacitive reactance to the circuit. We already have inductive reactance. Now we are adding capacitor. Because of the capacitor, we will have capacitive reactance as well. This is also kind of resistance. So it means it will also consume some energy, but at the same time, it reduces the angle between the voltage and current. So it improves the efficiency. So even though you increase the power factor, you increase the current drawn from the source because you are adding extra resistance, reactance to this circuit. Anyway, this is the trade-off. We have to accept it. So now we have to find the capacitive reactance. in the circuit, the same circuit, Xc is equal to 1 divided by 2 pi Fc. We know all the values. 2 pi F is the applied frequency. C is the 70 microfarad. Yeah, I think it's a 70, not 10. So please make sure this is correct. The value is correct. So now we find this reactance value using this formula. And now we have to find the total impedance value. Impedance is equal to the same formula what we have used, R square plus XL minus XC whole square root, the whole square root. So apply the values and you will get the impedance value. So now you have to find the new power factor value. New power factor means after adding the capacitor is equal to R divided by Z. R value we know that is the true power consumed by this R. R is 100 and then the Z is 106.8. So now the new power factor value is 0.9363. This is the, you can see it was 0.7985. Now the new value is 0.9363. It means we improve the power factor by adding this capacitor. And current flowing through the circuit, again use the Ohm's law. V is equal to IZ. I is equal to V divided by Z. V is 120 volt. And divided by Z we have found just before. So you can use this. So you can find the current value. And the previous calculation, we have also find the current value, right? So the current value was 0.958 amps. But here you can see the current value is more. The current value is 1.123. So it means the current value got increased from 0.9 to 1.1. So it means you are drawing more current from the source. It means you are paying more bill for the energy. So that is the problem. But anyway, we have to improve the power factor. So adding capacitor will introduce capacitive reactance to the circuit. It means it will consume more current. Even though you increase the power factor, but you also increase the current drawn from the source. This is the trade-off. Just like when you design the chip integrated circuit, you are reducing the size of the circuit, and also you want to improve the speed, the performance of the chip, but you want to reduce the power consumption. So this is always a big challenge actually. So this is always inversely proportional. So if you increase the performance, then the power consumption will be high. But if you reduce the power consumption of the chip, then it will affect the performance. So that is the trade-off. So we always have this problem in the engineering. If you want to improve one thing and you have to sacrifice on something else.